Welcome to our lesson on analyzing graphs and functions. Today, we'll cover three important topics: analyzing graphs of functions, piecewise defined functions, and the algebra of functions, including composition. Let's look at what we'll cover today. First, we'll learn how to analyze graphs of functions. Next, we'll explore piecewise defined functions. And finally, we'll study the algebra of functions and composition. Let's begin with analyzing graphs of functions. When we analyze a graph, we're looking for key features that tell us about the function's behavior. Let's consider a continuous function with some interesting features. Here's the graph of a function. We'll use this to demonstrate the key aspects of graph analysis. The first thing to identify is the domain of the function. The domain is the set of all x values where the function is defined. For this continuous function, the domain appears to be all real numbers or negative infinity to positive infinity. Next, we identify the range, which is the set of all possible y values that the function can output. For this function, we can see that the y values range from this minimum point here to infinity. So the range is approximately from negative 1.5 to positive infinity. Now, let's identify critical points, such as local maxima and minima. The function has two local maxima, here, and one local minimum, here. At these points, the derivative of the function equals 0. We also want to identify inflection points, where the concavity of the function changes. At an inflection point, the second derivative equals 0. This function has inflection points approximately here and here, where the curve changes from concave up to concave down, or vice versa. For this function, we can see it's continuous everywhere, which means there are no jumps or holes in the graph. A function is continuous at a point if the left-hand limit equals the right-hand limit, and both equal the function value at that point. Now, let's move on to piecewise defined functions. A piecewise function is defined by different formulas on different intervals. Let's look at an example of a piecewise function. Here we have f of x equals x squared minus 1 when x is less than 0, 3x plus 2 when x is greater than or equal to 0 and less than 5, and 7 when x is greater than or equal to 5. Let's graph this piecewise function to understand it better. For x less than 0, we graph x squared minus 1, which is a parabola. For x between 0 and 5, we graph 3x plus 2, which is a line. And for x greater than or equal to 5, we graph the constant function 7. To evaluate a piecewise function at a specific point, we first determine which piece contains that point. For example, to find f of negative 2, we use the first piece since negative 2 is less than 0. So, f of negative 2 equals negative 2 squared minus 1, which equals 4 minus 1, which equals 3. Let's try another one. To find f of 3, we use the second piece since 3 is between 0 and 5. So, f of 3 equals 3 times 3 plus 2, which equals 9 plus 2, which equals 11. An important aspect of piecewise functions is continuity at the boundaries between pieces. Let's check if our function is continuous at x equals 0, which is a boundary point. The left-hand limit as x approaches 0 is the limit of x squared minus 1, which equals negative 1. The right-hand limit as x approaches 0 is the limit of 3x plus 2, which equals 2. Since these limits are not equal, the function is not continuous at x equals 0. Similarly, we can check continuity at x equals 5. The function is continuous at x equals 5 because both the left and right limits equal 7. Now, let's move on to our third topic, algebra of functions and composition. When we have two functions, we can combine them in various ways. Let's start with basic function operations. Given two functions f and g, we can form their sum, difference, product, and quotient. Let's look at an example with specific functions. We'll work with f of x equals 2x minus 1, and g of x equals the square root of x plus 3. Let's find the sum of these functions. The sum f plus g of x equals f of x plus g of x, which is 2x minus 1 plus the square root of x plus 3. The domain of this sum is the intersection of the domains of f and g. Since f is defined for all real numbers and g is defined for x greater than or equal to negative 3, the domain of the sum is x greater than or equal to negative 3. Now, let's find the product of these functions. The product f times g of x equals f of x times g of x, which is 2x minus 1 times the square root of x plus 3. Again, the domain is x greater than or equal to negative 3. Now, let's explore function composition. Composition of functions f and g, denoted as f composed with g, means applying g first, then applying f to the result. Mathematically, we write this as f of g of x. Let's compute f composed with g for our example functions. We have f composed with g of x equals f of g of x. We first compute g of x, which is the square root of x plus 3. Then we plug this into f. So, f of g of x equals 2 times the square root of x plus 3 minus 1, which simplifies to 2 times the square root of x plus 3 minus 1. The domain is x greater than or equal to negative 3, which is where g of x is defined. Now, let's compute g composed with f. We have g composed with f of x equals g of f of x. We first compute f of x, which is 2x minus 1. Then we plug this into g. So, g of f of x equals the square root of 2x minus 1 plus 3, which simplifies to the square root of 2x plus 2, which can be further simplified to the square root of 2 times the square root of x plus 1. For the domain, we need 2x plus 2 to be greater than or equal to 0, which gives us x greater than or equal to negative 1. Note that the composition f composed with g and g composed with f generally give different functions with different domains. Function composition is not commutative in general, meaning f composed with g is not equal to g composed with f. Let's recap what we've covered today. We've learned how to analyze graphs of functions by identifying domains, ranges, and key features like maxima, minima, and inflection points. We've explored piecewise defined functions and how to evaluate them at specific points and check for continuity at boundaries. Finally, we've studied algebra of functions and function composition, seeing how to combine functions in various ways and the importance of tracking domains carefully. Remember these key strategies. Always track domains carefully, simplify and check for new restrictions at each step, and for piecewise functions, treat each region separately and examine boundary behavior for continuity. Thank you for watching. I hope this video has helped you understand these important concepts in analyzing functions.